So we are now familiar with the definition of velocity, dx dt, and the definition of acceleration, a is equal to dv dt. With those two definitions, we are going to derive all the equations of motion that we can use to describe one-dimensional motion. So let's start with the first one. I'm going to use the scalar version. So a is equal to dv dt. I'm going to multiply both sides by dt. Since I multiply both sides of the equation by the same term, I don't change that equation. So this is equivalent to a dt is equal to dv. And then I'm going to integrate that equation. Now, at this particular step, the only way that I'm able to integrate this is if a is either a constant or a is a function of time, because a shows up in an integration with a dt. So that's the only two possibilities that would allow me to integrate this. In this course, we will have the case where a is a constant. So if a is a constant, that's going to be my assumption. I can now take out that term out of the integral. So I have a dt is equal to dv. Now here's the recipe. Whenever we're dealing with an integration, in physics what we do is we set up the initial condition at the lower bound of the integration, and since we want to keep and get the equation of motion, we will always put the variable on the top bound of integration. So the initial value of the velocity will be our v initial, which we usually write as v naught. So v naught is the same as vi that we used earlier. Similarly for t, the initial value for time is t naught. Now what we usually do in this course is that we will always start our stopwatch and start measuring time when the process starts. Therefore, we will always have the case where t naught is equal to 0 seconds. Therefore, whenever we see an integral with a dt, we usually write the initial value of time, which is always going to be, in our cases, to simplify the algebra, t naught is equal to 0. So I've just used the initial condition. Now the boundary, the final condition, in order for me to get the equation of motion, I don't want to put a specific value, I want to put the variable. So since I have a dv here, I'm going to put v on the top. But if I do this, mathematically we are going to have a problem because this variable v is usually or sometimes called a dummy variable, which means that after you integrate, it should disappear. So we cannot have the same variable on the top and in front of the d. So we're going to change its name and I'm going to put a prime. So my v prime will disappear after I evaluate my integration between v and v naught. Similarly, when I see a dt, I'm going to put my variable on the top. I'm going to put t. And for the same reason as the v case, I cannot have the same variable in both places. So I'm going to recall and rename my dummy variable t prime. So that after I integrate my left-hand side, my t prime will disappear and it will be evaluated between t and 0. So those are very, very easy integration. dt prime will give me t prime, which I need to integrate between or evaluate between the final value and its initial value, or my variable t and the initial value t naught, which is 0. And the right-hand side is exactly the same case. I will end up with v prime, which I then need to evaluate between v and v naught. So I can evaluate this parenthesis, which gives me a times t minus 0 is equal to, this will become v minus v naught. And therefore I can rewrite this as v is equal to v naught plus at. This is my first equation of motion. From here, let's keep going. Now I'm going to use v is equal to dx dt. I'm going to use the same technique as above. I'm going to multiply both sides of this equation by dt. Therefore, this equation becomes v dt is equal to dx. Similarly, I'm going to integrate both sides. And at this stage, I have to ask myself the exact same question as before. The right-hand side is easy to integrate, but the left-hand side can only be integrated if v is a constant, whoops, or v is a function of time. Let's look at the first case, and then we'll do the second case after. Let's look at the case where v is a constant. So for the case where v is a constant, which means that there is no acceleration, then we can take the v outside of the integral, and this becomes v dt is equal to integration of dx. At this stage, we need to put the initial condition. So here my variable is x, so my initial condition is x naught. Here my variable is t, therefore my initial condition is t naught, which will use 0. On the top I will put my variable. I have a dx, therefore this is x, and again I'm going to switch my dummy variable name. And similarly, I have a dt, therefore I'm going to put my variable t on the top, so that I would obtain the equation of motion between v, x, and t. So I can integrate the right-hand side, the left-hand side and the right-hand side. This will give me t prime evaluated between t and 0, and on the right-hand side, x prime evaluated between x and x naught. This will give me v times t minus 0, which is t, and on the right-hand side, x minus x naught. Therefore, x is equal to x naught plus vt. This is my second equation of motion. But we have to be very careful and remember that this made a major assumption, which is that we can only use this equation if and only if my acceleration is 0 and therefore my velocity is a constant. And you'll notice that in this equation there is no trace of v naught, because it is assumed that v naught is the same as v, which means that a is equal to 0. So keep in mind, you can only use this equation only if the acceleration is 0. If the acceleration is not 0, we cannot use this equation. Okay, now let's look at the second case, where v is a function of time. V dt is equal to dx. And here we'll use the results of the previous step, which is this one. Obviously, if v is equal to v naught plus at, then really v is a function of time, which means that as time changes, the value of v will change as well. So this is the functional form of this v that we will use. So since we know that v is equal to v naught plus at, which is for the case where, in this case, a different from 0, we will going to plug this functional form into our vt, and we have v naught plus at is equal to times dt is equal to integration of dx. Similarly, we're going to put the initial condition. I have dx here, therefore initially I start at x naught. Here my variable is t, therefore I'm going to start at t is equal to 0. Similarly, the top bourne of integration will become my variable, because I again want to obtain the equation of motion. So if I see a x here, this will be x. I have a t here, therefore this will be t. And again, I need to change my dummy variable, so it's different from my upper bound of integration. Let's look at this equation. This equation is the same as before. This will give me x prime, evaluate between x and x naught, which will give me x minus x naught, no problem. Let's look at the right hand side. It looks complicated, but really it's quite simple. This is nothing different from, say, this. That we used to in calculus. In this integral, our variable is t prime. Therefore, as far as this integral is concerned, everything else can be treated as a constant. Therefore, v naught is a constant, a is a constant. So this integral is nothing different from integrating, say, this one, where we would end up with 3x plus 2x2 divided by 2, evaluate between my two variables. We know how to do this. So let's do it using the variable v naught, a, and t prime. V naught is a constant, therefore this will become V naught times T prime. This is a polynomial of degree 1, therefore this will become a T prime squared divided by 2. And this will be integrated between T and 0. As we evaluate this integral, we will obtain V naught. I will evaluate and replace, every time I say T prime, I will put my T plus a T squared divided by 2 minus the same equation evaluate at t prime is equal to 0, which will give me 0 plus 0. So I end up with, if I rearrange the term, I'm going to put the x naught on the other side. X is equal to x naught plus v naught t plus 1/2 at squared. This is going to be my third equation of motion. So let's summarize. My first equation of motion was giving me the velocity as a function of time. My second equation of motion was giving me my position as a function of time, and this one, remember, can only be used if a is equal to 0, while the first one could only be used if a is a constant. And the third one is the second functional form of x with respect to time, but this case not for a is equal to 0, but for a non-equal to 0 and being a constant. So v is equal to v naught plus at. This is true and only true if a is a constant. Then we add two more. X is equal to x naught plus vt, which is true only if a is a constant and equal to 0. And the third one is x is equal to x naught plus v naught t plus 1/2 at squared, and this one is true if a is still equal to constant and doesn't have to be equal to 0. Now, obviously, you will see clearly that if you set a is equal to 0, so you pick a particular case, a is a constant, you pick that special value of a being 0, you plug it into this equation, and you end up with v is equal to v naught, which confirms the fact that if there is no acceleration, the velocity is invariant. Similarly, you can play the same game on the last equation. If you plug a is equal to 0 here, you will end up with the second equation. So everything is consistent. Now what I would like to do is, I would like to get the equation of motion between the velocity, the position, the acceleration, but without time. All my equations have time in it. If I have problems where I know nothing about time, I need to be able to approach this problem with equation that doesn't involve time. So what I can do from here is use equation 1, solve for the time, and then plug that time in back into equation 3. Let's see what happens when we do this. Equation 1, v is equal to v naught plus at, and I'm going to solve for my variable t from here. So t will be equal to v minus v naught divided by a. And then I'm going to plug and replace my variable t in equation 3 with this functional form for t. I'm going to end up with x is equal to x naught plus v naught t. Whenever I see a t, I'm going to plug this, v minus v naught divided by a plus 1/2 a times t squared, v minus v naught divided by a, everything squared. Let's expand and do the algebra. X equal to x naught. Here I'm going to pick up v naught times v divided by a. The second term is going to be minus v naught squared divided by a. Then the next term, I'm going to have three terms because I have a minus b squared, so I'm going to have a squared plus b squared minus the cross term, 2ab. I can simplify one of my acceleration because I got 2 in the bottom, I got 1 on the top, so 1 will go away. So my first term will be v squared divided by 2a. The last term will be v naught squared divided by 2a. And my cross term will be minus v times v naught twice divided by these 2, so the 2 will cancel out, and the a still survives. Okay, let's look at who's what. Oh, this one and this one, bang, simplifies. What else? This one and this one, we can combine them. All I need to do is multiply this by 2 and 2. So those two terms, if I put them together, will give me minus v naught squared divided by 2a. And then I got this term, which is still here, plus v naught divided by 2a. So I can combine the two. V squared minus v naught squared divided by 2a. That's all there is on the right hand side if I move this term on the left hand side. So I end up with x minus x naught is equal to all this. So what I can do from here is multiply the whole equation by 2a, move the v naught squared on the other side, and I end up with v squared is equal to v naught squared plus 2a x minus x naught. And this is my equation of motion of the velocity as a function of position only without any time. So this is nice whenever I have a problem where I don't have any information about time, I can always use that one. There is a fourth, wait, how many did I do? A fifth, sorry. A fifth equation of motion that is sometimes useful. We're going to use the same strategy as for this equation of motion, except instead of solving for the time, I'm going to solve for the acceleration. So that I'm going to end up with an equation of motion between x, v, and t without anything about, or no information about a. So from this equation, v is equal to v naught plus at. I'm going to solve for a. A is equal to v minus v naught divided by t. And similarly, I'm going to plug it back into my third equation, which was x equal to x naught plus v naught t plus 1/2 at squared. So I'm going to replace my a with this. This is going to give me x. I'm going to move the x naught on the other side. Minus x naught is equal to v naught t plus 1/2 times this, v minus v naught divided by t times t squared. From here, I can simplify one of the t's. Let's expand this term. I'm going to have x minus x naught is equal to v naught t plus 1/2 of vt minus 1/2 of v naught t. What can I do from here? Oh, I recognize that this term and this term are similar, I can combine them. This will give me plus 1/2 v naught t, and then I still have this one, which has a very similar functional form, so I can combine them. So I'm gonna factorize 1/2 and t. So I end up with v naught plus v t, and this is x minus x naught. And you recognize that this is nothing else than the average velocity. So this equation is nice because it doesn't explicitly use the value of the acceleration. Obviously, if the acceleration is 0, then v is equal to v naught. We end up with 2v, the 2 will cancel out, and we are back with x is equal to x naught plus vt. Okay, so in summary, we've derived how many? Five equations of motion. First one, v is equal to v naught plus at. And this is true if a is a constant. Then from there, we also use a is equal to dv dt to get this. Then we use v is equal to dx dt. We had two cases. First case, a is still a constant. So the general case will give us x is equal to x naught plus v naught t plus 1/2 at squared. And this would be x as a function of time. And then we had the simplest case where a is equal to 0. So this term disappears, and we end up with x is equal to x naught plus v naught t, which is the same as v because a is equal to 0. And this is true and only true if a is a constant and equal to 0. So really, this equation comes from this one. Then we did a little bit of algebra because we wanted the equation of velocity, acceleration, position without any occurrences of time, and we ended up with v squared is equal to v naught plus 2a x minus x naught. And then for good luck, we derived the fifth one, which gave us, so this was v as a function of x, which again is true if a is a constant. Then the last one was x equal to x naught plus 1/2 v naught plus v times t, which is again x as a function of time for a being a constant. Those are the 5 equations of motion that we will be using this semester. Mostly the first 4. The fifth one might occur in some cases.